Hello everyone, myself Rashmi. I am an assistant professor in physics department at XRD Technique University, Sirsa. So this is just an introductory video of what I am going to discuss in my next video. So in my next video, my topic of discussion will be X-ray diffraction. So in the next video, you will know what is the diffraction phenomena, how one can produce X-ray diffraction, that is, what are the conditions required to produce the diffraction phenomena, and how X-ray diffraction is different from the diffraction of light, and also how X-ray diffraction can help us to determine the structure of the crystal. So if you are interested in the topic, you can join in my next video. Thank you very much.
Hello everyone, myself Rajni. I'm an assistant professor at XRD Technique. Today we are going to discuss about the topic X-ray diffraction. So let me just give you a brief introduction of what we are going to discuss. First we will discuss about the diffraction phenomena. Then we will discuss about how diffraction occurs, that is, what are the conditions required to produce diffraction phenomena. Then how light diffraction is different from the X-ray diffraction, and then how X-ray diffraction will help us to determine the crystal structure. So without wasting any time, let's begin this topic. So what is diffraction? Diffraction is basically the phenomena of bending of light through the corners of any obstacle or aperture. Now, first thing you should know what is an obstacle and what is an aperture. Obstacle is something which restricts the path of the light. That is, if an obstacle is placed, light would not be able to pass through it. So, across that obstacle region, there will be no light. If there is an aperture, light will pass through the aperture. Clear? So, that's the basic difference between obstacle and aperture. So, whenever an obstacle or aperture is placed in the path of the light, then what will happen? This light will either not pass through the obstacle, that means it will bend through the corners of that obstacle, or that means there will be a region where the light should not reach, but the light will reach there. Similarly, the case will be with the aperture, that means the light will bend through the corner of the aperture, so that means the light will exceed in the region where light should not reach, but it will reach in that region. So let me just tell you how it will happen. Let me move to my next slide first. So this is a pictorial representation of diffraction phenomena. So see, if you have a source of light here, this is the source of light, and this is an aperture. Aperture is something which allows the light to pass through. So you see here light can pass through it. And this is the screen, and this is the intensity profile. I will tell you about the intensity profile also, but first we will discuss about the source. For the diffraction phenomena to occur, usually we use in our laboratory a monochromatic source of light, but here you can consider it as a normal source of light. It can be sun or any other source of light. So you are using any source of light here. Light, if it was traveling into a straight line path, that means if it travels into a straight line path, then across the corner of this aperture, light would travel like this. That means across this region, these are the two corners of our aperture. That means this is the region where light should reach, from here to here. In this region there should be light, and across this region there should be no light. Let me just use my pen. So this is the region where there should be light, but across this region, above this region and below this region, there should be no light if the light was traveling into a straight line. But you see, as through the diffraction phenomena, when light crosses this aperture, through the corner of this aperture, that means here, the light will start bending, and it will start, suppose from here, it will move like this. You should have drawn a straight line, that means light should have bent. So that means there will be some light in this region also, and the intensity of this light goes on decreasing as we move away from the aperture. That means corner as we move away from this line, light will start, the intensity of light will start decreasing. So that means the region which is called geometrical shadow region. Shadow region means the region where there is no light. So since the light has bent through the corner, there will be light in the region of the geometrical shadow. So this phenomena is known as diffraction phenomena. I hope this is clear to all of you. So now we will discuss how this diffraction phenomena occurs. That means what are the conditions. You usually don't see that light is bending through the corner. You won't observe this thing, but you can observe what you can observe when you are, suppose you have light across a room and you open the door and you keep it half open, then the light should reach only through the region of the door, which is the path provided by the door which is open. But when you see, there must be some light outside that region also. This phenomenon is known as diffraction. But how and when this thing will occur? That means this light will cross the region of the geometrical shadow. When will this occur? When there is some certain condition which is satisfied by the object and the light. So let me just move to my next slide. I will tell you later. So this is, suppose, as we know, light is an electromagnetic wave which is a transverse wave, and a wave have a wavelength. So this is a wave, and this region of two crusts, the distance between two crusts is known as the wavelength of the light. So when the wavelength of the light used is approximately equivalent to the size of this aperture, that is means the width of this aperture is equivalent to the wavelength of light, then only this diffraction phenomena will occur. That means size of your object is equivalent to the wavelength of the light, that diffraction phenomena occurs. As we know, in our visible region, the wavelength of light is approximately 300 to 700 nanometer. That means if an obstacle or aperture has approximately size in this range, then diffraction phenomena will occur and you will see the diffraction pattern. That means light in the region where there should be no light, that is the geometrical shadow region. So that means there will be some intensity of light in the dark region also. Now suppose if this is a double slit, Young's double slit experiment basically. Here what we have, this is the source of light, it's a single slit, and across the slit here must be some object which is a source. From the source, light is crossing this aperture. In front of this slit there is another slit, second slit, where there are two holes, that is there are two apertures in front of this light, and this is the screen. What will happen now from here? The source is emanating light and this light crosses this slit 1. From this slit 1 there are two sources, S1 and S2. From these two sources light is again emanating, and these two sources will act as two coherent sources. Now the concept arises, what are two coherent sources? Coherent sources are basically the sources which are derived from the same source. Here we have only one light source used. If we have used two light sources here, suppose one here S1 and another here, sorry, not here, if we use another source, one source here and another source here, then it will not have been a coherent light, because the light has been derived from two sources. The light across the source S1 is coming from this source, and the light across the slit S2 is coming from this source. So that means these are two another independent sources. Independent means which are emanating their own light. So suppose if you have two torch, basically for this experiment we should use monochromatic source of light, but if you are using a normal source, this pattern should have been changed, but we will talk about that later. So if you are using two sources of light, then the light would have been independent. So the wavefront that these light would have generated, that would have been, they would not have any correlation between them. So the phase difference between them should not be constant. Under that circumstances, sometimes suppose this wavefront is here, for the another light that wavefront should be here, or there may not be any relationship between the two wavefronts. because they are independent. That's why these two light sources would not be coherent. So for the diffraction phenomena to observe, we use coherent sources. That's why a single source is placed here, and from that single source we have created two coherent sources, that is, which are derived from the single source. So there is only one source, and in front of that there are two slits which are acting as two coherent sources. So from these sources, these are the wavefront that are generated. One is crust and the second one is trough, then again crust and then again trough. From here, when crust of one wavefront fall over the crust of another, that means the crust is basically the maxima part of the wavefronts. Let me just move back to the slide so that we can know about this. So this point where the intensity of light is maximum is known as the crust, and the point where the low lies, that is known as the trough. Clear? So when crust of one wave fall over the crust of another, that means the two intensity will be the maximum intensity. So the resultant intensity of these two interfering pattern will be the intensity doubled. So that means the intensity has increased. And when trough, that is low energy, is falling over the low, there will be a dark region. That means that will be a destructive interference. So here in our experiment, whenever crust of one wave fall over the crust of another, there will be bright region. That means there will be intensity more than any of the source. And when trough of one wave fall over the trough of the another, then again there will be maximum intensity, but in the opposite direction. So when crust of one wave fall over the trough of the another, the light will be minimum. So there will be two regions. One is known as bright. Bright is when crust of one fall over the crust of the other, when trough of the one fall over the trough of the other. And we will observe dark region when crust of the wave, one source, will fall over the trough of the another, or trough of one wave fall over the crust of the other. Then we will observe interference pattern. Clear? So that means this is the diffraction pattern, and the intensity pattern will not be uniform. That means all the bright fringes will not be of the same intensity. Only the central bright fringe, we call these fringes. So only the central bright fringe will be called as principal maxima, because its intensity will be maximum, and all the other, because here the intensity of light is keep on decreasing, because crust of one is falling over not on the crust of other, or trough of one is falling over the trough of the other. Only this is the place where crust of one wave is falling over the crust of another, and trough of one is falling over the trough of the another. So this region is called the maximum brightness region and is known as the principal maxima. And the region next bright ring or fringe which is appearing is because of crust of one is falling over the, not the crust. Crust is the region where the light intensity is maximum. Here you see, this is not the crust part. Crust part must be the central region of this. So that means this region is not the crust part, somewhere between the crust and trough. Suppose this is the maxima, crust of one is falling over here. For the second, this part of is falling over here. So that means intensity will increase because both are positive part, but the intensity will be less as compared to the central maxima. Clear? So that means all the dark fringes, all the next brighter fringes will have intensity, but they will be bright because they have high intensity, but that intensity will be lesser than their preceding fringe. So that's called the diffraction phenomena. So now we discuss how diffraction of light is different from the X-ray diffraction. But before that, we must know what is X-ray diffraction. So you must know, whenever we observe light diffraction, we would observe a pattern of bright dark fringes, and these fringes will have intensity difference. That means one fringe is very much bright, that is the central fringe, and then as we keep on going away from this bright fringe, another bright fringe will have intensity lesser than the central, and the another one, the second bright fringe or the second principal maxima, will have lesser intensity as compared to first maxima. Clear? So next we will discuss about the X-ray diffraction. So as I have told you, there is only one condition for diffraction, that is the size of aperture or obstacle should be equivalent to the size of the wave, that is the wavelength of that wave. If these are two comparable, then diffraction phenomena will occur. So as we know, in in crystal, the atoms are separated. You see, this is this atomic separation, or you can say the interplanar spacing, that is the two atom, the separation between two layers. Basically, interplanar spacing is different from the atomic spacing in a crystal. Interplanar spacing is there are two layers which are separated by a distance d, and and lattice parameter is basically the primitive cell lattice parameter of a crystal, this distance. Okay, so in the crystal there are many layers of the atoms which are arranged in a regular pattern, and the separation between two layers is known as the interplanar spacing, and this interplanar spacing is basically of the order of few angstrom. So that means 10 to the power minus 10, suppose 1 into 10 to the power minus 10 or 2 into 10 to the power minus 10, depending on the lattice you are using, that means which element are creating this lattice. So basically in this crystal you see these atomic layers are arranged, and this interplanar spacing, which is d, that is approximately 10 to the power minus 10 meter. This is the size of interplanar spacing for all the crystal lattice, approximately around this. Also the X-ray also has the wavelength in this region, that is 1 to 10 nanometer is the size of X-ray. So since the X-ray also have wavelength comparable to this, X-ray is also lying in the region few angstrom, and also the interplanar spacing, they both are comparable. That means if X-ray is falling over some crystal, it will diffract the crystal. That means the light falling over the crystal, it will get diffracted. That means it will bend through the corner of this. This atomic site will act as the diffractor, or you can say this will act as the obstacle for the X-rays, and we will observe a diffraction pattern. Okay? So from this diffraction pattern, now we will discuss how this diffraction pattern is going to help us determine the crystal structure, and also how this X-ray diffraction is different from the light diffraction. Okay? So in the light diffraction we use a light source and a diffractor, that is either an obstacle or aperture. When this light is falling over the obstacle or aperture, it will bend through its corner and it will create a diffraction pattern, that is a bright dark fringes, and human eye can see the visible light. So that means when we use light diffraction, basically we are using a light region that is falling in the visible region, an electromagnetic wave which is falling in the visible region. So the diffraction pattern will also consist of bright dark fringes. Usually we use a monochromatic source, and most of the light are in the red in color. So you will observe red light, and then there will be dark region, red light, and then there will be dark region. So light diffraction will consist of bright and dark fringes. But in this electromagnetic spectrum that we have, only the visible rays have visibility, that means visibility to human eye. We can only recognize the light that is falling in the visible region, but X-ray are not visible to human being. That means when X-ray will strike the crystal lattice and it will strike the atom and it will get diffracted, the diffraction pattern will be observed, but how will human eye see it? That means that's the difference basically in the X-ray diffraction and the light diffraction. In the light diffraction you can observe that pattern and you can make your measurements across that experiment. But in the X-ray diffraction, the light is not visible. That it's not the light. We should call it X-ray. The X-ray is not visible to you. That means the diffraction pattern would not be visible to you. So how would you introspect this diffraction pattern, analyze this diffraction pattern, and get the inference of the crystal structure through the X-ray diffraction? So that's why X-ray diffraction is different from the light diffraction. In light diffraction you will use basically that you must have done in your BSc experiments also. You basically use a monochromatic light, that is either you use some laser, usually helium-ion laser is used. So you are using a helium-ion laser and you are placing it in front of some diffractor, that is a slit. Basically people use diffraction grating for this to create the diffraction pattern, and this slit diffracts the light and you observe the diffraction pattern in a spectrometer where there are separate slits of different color. If you are using suppose a monochromatic light which is red light, then you will observe red light, red slit, and then dark region, then again red slit and dark region. All these red slits which are moving away from the central slit will have intensity lesser, so intensity will keep on decreasing from the central maximum. But when you are using X-ray diffraction phenomena, you are using a crystal as the diffractor. That means instead of diffraction grating we are using a crystal, and instead of light ray we are using X-ray source. X-ray source are basically Roentgen tube from where you generate X-ray. So there is a source, again like diffraction pattern, but here in this experiment of X-ray diffraction, all the requirements of your experiment changes. There is requirement of a source, a diffractor and a screen in both the experiment, but source used for X-ray is different from source used for light ray. The diffractor used for X-ray is different from the diffractor used for the light ray. Also the screen used for the observation of the X-ray diffraction pattern is different from the screen used to observe the diffraction pattern for the light ray. What is the difference here? Because in the light we can observe the diffraction pattern, we can see it by the naked eyes. That means only if we suppose you take a cardboard and paste a paper, white paper over it, and you place it in front of the light source and you will observe the diffraction pattern over that paper. But if you use X-ray and you are placing the same cardboard there, you will not observe any diffraction pattern because X-ray is not visible to you. That means what will you use there? You must use some other source, not source but the analyzing instrument that must be different from that used for the light ray. So basically for the X-ray diffraction we use another detector which is Debye camera, which is specially designed to observe the X-ray diffraction pattern. And since that light is not visible to you, so how would you determine that your light is diffracted? Suppose this is our incident light and this is our diffracted X-ray. Clear? So in your light experiment, suppose let me just move to the slide so that you must know. Here we have used light source. This is the bright fringe. If I place my spectrometer or my spectrometer's eyepiece cross wire over here, then you can observe the reading of this dark fringe. Also if you place your spectrometer eyepiece cross wire over here, you will get the difference of the two readings and you will get the position of these two dark fringes. But if you are using X-ray, you don't know where this light is coming from and where this light is going. So what we do, since the X-ray source and the diffractor, this is the incident beam. So what we do, the incident beam act as give you the angle of the diffraction basically, and this is determined from the Bragg's law. I think all of you are aware of the Bragg's law, because Bragg's law you must have studied it in BSc also. So if you want I can explain this also, but I will have to make another video for this. So here I am only telling you how this have happened. Also if you don't know, this is something interesting here. We are calling it diffraction, but when you talk about the Bragg's law, you say Bragg reflection spots. Why do you call it reflection? Because the diffracted spots are basically the reflected spots. and how it will occur. If you want to know about it, you must write to me in the comment box. I will definitely try to explain this also, why this X-ray why these spots, that is the diffraction spots, are called as reflection spots, Bragg reflection spots. If you want to know about it, you must write me in the comment box. But I am telling you here that since the intensity of the reflected spot is maximum, so the diffracted ray are basically the reflected ray. So reflected ray, if you observe here, you will get from the Bragg's law that n lambda is equal to 2d sin theta, which is the Bragg's condition. So if we know the wavelength for a known wavelength, if we know exactly the wavelength of X-ray, n is the order of the diffraction pattern. That is, you for example, in the light diffraction phenomena, you observe bright fringe, then dark, then bright, then dark. So that bright fringe basically was your first order spot. The first your first bright fringe, that is the central maxima, is the first bright spot. Then the first maxima is known as, this is the second spot, and then second maxima will act as third spot. So that will give you the order of the diffraction pattern. So this is the diffraction order of diffraction pattern. If you know the order of diffraction pattern, if you know the wavelength of light, and if you know this angle of diffraction, then you can calculate D, which is the interplanar spacing. So this will give you the information of the lattice parameter also. That we will discuss later, but first it will give you the interplanar spacing, that is the difference or the distance between the two crystal planes. So in the powder diffraction pattern, basically we use the crystal, or we use the sample in the powder form. That's why it is called the powder diffraction pattern. Powder diffraction. So in the powder diffraction, as we use the powder, and in powder there will be small granules of the crystal, and each granule will be oriented in some different direction or random direction. So when X-ray is falling over the crystal of different granule of the crystals, they will be oriented in different direction, and you will get the different D spacing for the crystal. So if you are using powder diffraction, if you are using a monochromatic light and you know the order of the diffraction, and the angle of diffraction is measured from the Debye-Scherrer camera, that you can calculate from the Debye-Scherrer camera, which is your detector, then you can calculate the interplanar spacing for almost all the crystal planes. So next, if we know this crystal interplanar spacing, then for a simple cubic lattice, you can calculate the lattice parameter also. Here D is the interplanar spacing, A is the lattice parameter, and H, K, L are the Miller indices of the crystal. So from the X-ray experiment, you get to know the interplanar spacing, and from this interplanar spacing you can calculate the Miller indices of the crystal can be known. You can know about it by the diffraction pattern. So if you are observing an X-ray diffraction phenomena, then you will observe different peaks. There is a graph plotted between the 2 theta value and the intensity value, and that intensity plot, all those peaks can be assigned to different HKL value, that is the Miller indices, by comparing it with the standard diffraction data, standard powders, and these data is stored in the JCPDS cards. So from the by comparing this interplanar spacing, these lattice parameters and all these specifications, peak positions and the intensity with the standard diffraction data of all the samples, you can compare it with that, and you can know about the interplanar spacing. And then from the interplanar spacing, as you are aware of the Miller indices of the sample for the particular peak and interplanar spacing also, then you can calculate the lattice parameter also. You can calculate the same for the other crystal lattices also. I have written only the formula for the simple cubic lattice, but for other lattices this can also be calculated. The formula will be different for the formula of lattice parameter will be different for different crystals. So this is about the X-ray diffraction phenomena. If you have any doubt, you can write to me in the comment box, and if you like my video, then you can share it with other people also, so that I'm not saying it for a publicity purpose, but if this video will be helpful for some students who are interested in knowing the concept of X-ray diffraction, then you can share it with the other people also. And if you have any doubt, you can write to me. And thank you very much for watching this video. Thank you.